see, we have seen the, huh? Can you tell me? Same thing, right? Yeah. So we have seen the counters where there is a arrangement of like the output of the last is given to the input of the first. Such kind of counters, when you have such kind of patterns where the bits are getting shifted, it's like a simple shift register, isn't it? So such kind of counters are called as ring counters, okay? And if the output is not coming, instead of coming from the non-complementary output, if we take, now there is a possibility that we can connect the complementary output to the input of the first. That is also very well possible. That kind of counters are called as a twisted ring counters, okay? I mean, just because it's twist which is happening, or it is also called as a Johnson's counter. Now these are the names which you will find in the text, but you don't need to worry about that. You just need to look at the pattern, how they respond, and then act accordingly. See, what I'm saying is this: if you, these are the, I'm assuming that these are the D flip-flops, data flip-flops, D, Q, Q0, Q1, and Q2, Q2 bar, Q1 bar, Q0 bar, and so on. Now, what if I do connect output of this to the input of first? If I do like that, such counters are called as a, although it may be a D, it may be JK also, okay? So such counters are called as a ring counters. Can you tell me its mod? Can you tell me its mod? Mod of this ring counter, assuming the first state to be 10000, yeah? Huh? Mod 3, yes. So it's like a mod n counter. So all the ring counters are mod n counters. But what if we do something like this? Instead of connecting this, what I'm doing is I'm connecting this complement wala output to the input of 1. That also I can do. So such kind of counters are called as a, now that is not connected, okay? This is not connected, okay? I'll put a cross there. Now this is not connected there. In that case, this is called as a twisted ring counter. Or in that case, the count will be doubled. You will come to know. You practice a lot. That's homework for you to find it out that the count will be doubled. It's a mod n. Sorry. This is a mod n, and this would be mod 2n. This will be 2n states, and this is also called as a Johnson's counter. All right. There was one question based on this in the current GATE examination for 2 marks. I mean, see, these are simply the names. You should always remember that. Now, this counter can also be created using JK flip-flops. How that is possible? You connect both of this, okay, both of this, the outputs to the inputs of the next. So, what I'm saying is, using JK, you can very well design that something like this. JK, we have 2 inputs, 2 outputs. And if we do something like this, this again a ring counter using JK flip flop. So this is JK. JK, this Q0, Q0 bar, Q1, Q1 bar, J1, K1, J0, K0, J2, K2, Q2 and Q2 bar. And of course these internal connections are straightforward. This again a ring counter using JK. What if I interchange, if I give the complement to the normal of the to the J input and uncomplemented output to the K input, that becomes again a twisted ring counter. Okay. Homework for you is to verify the states. Now in the twisted ring, assume that the states are resetted 0 0 0 0 and then analyze the circuit and so on. So this is all about simple counters. Alright, is this clear? The analogy would be the same, the procedure would be the same. You will have to analyze step by step, states by state, and you just need to look at if they are connected like this. The uncomplemented to the J, complemented to the K, or in D case, it's like straightforwardly connected in the ring way. That is called as a ring counter. If it is the complement wala output is connected to the input of the first, that is called as a twisted ring. That's it. Nothing fancy about it. These are also the counters which are used. Just the states are although different, although the states are limited. We can only count till n. Number of flip flops jitna hai, or max up to 2n. But usual counters would count up to 2 to the power n, right? Maximum I'm saying. Alright. Let's go ahead. Now, okay, say for example I have designed a counter. Nice, okay. Assume that there is a box inside which it's a mod, and let's say anything, okay, it's a mod 5 counter, and if I have designed another counter, let's say it is mod 10 counter. Assume that I have cascaded these. And can you tell me what mod it would be if you consider it overall? Now I am saying is, now I am put all of both of these counters which are cascaded one after the other. Can you tell me the mod of this? First you should know what is mod. What is mod? Number of states. So for states, okay, for 5 states here and 10 states there. For each 5 state here, there will be 10 states there. So what is the overall mod, you tell me? 50, right? So it will be, if mod m and mod n are in cascade, so I will now generalize this. If they are mod n, let me write that. Mod m, mod n, then in cascade, and this overall becomes mod mn. M cross n. Can tell me what if I give a 50 hertz frequency here, or a clock cycle which is running at 50 hertz frequency? What is the output here? What is the output here? We have seen that if the input frequency is of some hertz, okay, what is the output of a mod m counter? You tell me. एक flip flop. Let's go one by one now. एक flip flop लिया. For each and every negative edge, it responds. That means every flip flop, you look at the points. काउंट शिफ्ट रजिस्टर शुरू करने से पहले अपन ने पॉइंट्स लिखे थे कुछ, देखो. Each flip flop acts as a what? Frequency divider. What is the frequency with which what is the division factor? Yeah, m. I mean it will be m, or divide by 2 counter. Each flip flop is acting as a divide by 2 divide by 2 frequency divider, right? Or you can say it as a you should not go with the flip flops, you should go with the states, because sometimes states may be deleted, right? I mean we may not go for complete states like from 0 to 7. If it is of 3-bit flip flop, we may not go from 0 to 7, we may limit ourselves to 0 to, let's say, 5. In that case frequency will be divided by mod m, right? I mean it will be divided by m. That means at the output of this you will get divided by m, at the output of this you will get divided by n, so overall will be divided by mn, right? So this you should know. Okay, I am expecting answers from you guys. मुझे बोलो कि इतना रिमेंबर करने की जरूरत नहीं है. मॉड m मतलब क्या? m के बाद स्टेट्स रिपीट होगी ना. Okay, now those states will be repeated, isn't it? How many states are getting repeated? So divide. Now if the input clock frequency is 50 hertz, these states will be repeated after m states. Okay, and for each of those states, that mod n in at output of mod m, mod n, the next counter will be dividing it further by n. Okay, so overall it will be divided by mn. That means now you tell me, what if this m is to okay, let it be 5 and 10 again. What is the output? You tell me. 50 1 hertz. Okay, 1 hertz. So output will be 1 hertz. Now I may go for this is not the only way to. Now this is how the frequency divider is operating in clocks, right? Suppose I need to divide design a clock. What do we do? This is one crystal. Okay, इस clock के अंदर एक crystal oscillator रहता है. हमने crystal oscillator देखे हैं, isn't it? It is a small crystal which actually fluctuates, which actually oscillates with very high frequency. Let that frequency be, now those clocks are designed in such a fashion. I have shown you a video in analog electronics class where I have said that they are tuned to some particular frequency in such a way that when further these frequency dividers are applied to those clock frequency, you will get a divided clock frequencies. Say for example, you need to count seconds. Okay, you require a clock which is actually counting seconds, right? The frequency will be quite higher. If you need to count minutes, it will be divided by, I mean, how much is the factor? 60, right? For each 60 seconds, it will require 1 minute to be counted. So there is how, there is where there is a demand for divide by n counter, right? I mean, frequency divider is required there. So it's not necessary to go for 5, 10. I may go for, let's say, 2, 5 and then 10. Okay, and very well all the factors here are possible. Okay, just need to remember that the output of a cascaded counters will be mod mn. That's it. That's the point to be noted. Is that okay? Clear? Let's go ahead. Let's go ahead. Now, very less time today. All right, I'll take small example. There is another application of what is called as a sequence or a pulse generator. Now there may be a demand. As a designer, you should be able to design any digital circuit. If there is a demand, say that you want to design a pulse, something like this. Let this be 1 0 0 1 0 0 0 and so on. I mean, you can take any example. let's say one more 0, or I will change this for a bit, 1 1 ले लेते हैं. That will show you a few more variation. You can take any example, no problem. Now let this be 1. Now what I am saying is, suppose you need to design a circuit which would generate this pulses. How that we can do? How can we do that? That means repeatedly it should generate this sequence. What is the sequence? 1 0 0 1 1 0 0 0 and so on. I mean, this is now repeated. After that 1 0 0 1 1 0 0 and so on, and this will go on continuously. Sometimes we may require to generate a sequence. Okay, then how that can be done? Let's see. Now one way, see, first of all you should determine how many outputs are required here, how many bits are required here, how many pulses are required there. How many pulses are required? Let's say 8, right? Now we want the sequence to be generated, as I said. I mean, series of, after 1 it should go to 0 0, then 1, then 1, then 0 0. It should go in the sequence, right? Now suppose we need to generate this. How that can be done? Let's see. Suppose now there are 8 states, right? 8 different pulses we need to generate, unique pulses. How many flip-flops will be required, you tell me? Four. As I said, it's a series, so how many flip-flops will be required? नहीं पता. Okay, take some flip-flops. Okay, let's take some toggle flip-flops. Only 3 is 8 है ना? 3 0 to 7. I mean, 3 flip-flops will be sufficient. Let's see how. Now let's see, let's say it is a T flip-flop, Q0 bar, and see here, see, मैं तो बहुत सिंपल वे में सोचूंगा. मुझे आउटपुट क्या चाहिए? 1, उसके बाद 0, उसके बाद 0 एंड सो ऑन. ये पैटर्न चाहिए ना. ये पैटर्न वी कैन ऑलवेज रिप्रेजेंट विथ रेस्पेक्ट टू some combination. We can always create this with some kind of combinational logic, and we want it to be generated one after the other. That means we can go for the counter. We just have to track the sequence, okay, one after the other. I mean, if it is 1, the next should be 0 and so on. We can take any counter, like a 3-bit counter we can take. I mean, the minimum required bits are only, minimum required flip-flops are 3 here. So what I can do is, I can simply write the states here, Q2, Q1, Q0, and write all the possibilities. 1 0 0, 1 0 1, 1 1 0, and 1 1 1. And assume that I put that in the box. Okay, ये मैं एक, हमको सीक्वेंस जनरेट करना है ना, मतलब आउटपुट कितना चाहिए आपको? Only 1. That means I want one output, okay, and which should go one after the other, like 1 0 0 1 0 and so on. Let's define that output to be F. initially I want what? 1. After that 0. After that 1, 1 1, no? 0 0 job is done. How? For this state, let the output be 1 first. Next state, let the output be 0. Now you tell me, now you should complete this. Can you complete this now? Complete the circuit now. How? Yes, very good. So you can very well form a K-map out of this and see how this sequence appears. Tell me quick. बोलो 1 0 0 1 1 all zeros. Yeah, tell me the logic. This is Q2 Q1 Q0 0 0 0 1 1 1 1 0 0 1. बोलो this can be combined. This is single. बोलो logic क्या है? हाँ Q F is equals to, बोलो फटाफट, Q और what is that? Q2 bar Q1 Q0. Is that okay? This is okay. That's it. Now what you need to do is you simply have to connect that to a OR gate. I mean 3 input, two how much circuit is required? 2 AND gates and 1 OR gate. 1 3 input, 1 2 input AND gate and 1 OR gate. 2 input OR gate. That's it. Job is done. Simple ना? मतलब अगर आपको किसी ने बोला कि ये सीक्वेंस टाइप के जनरेट करो, then you should be able to easily do that. Tell me the connections now. Q wait, at the output, no? At the output I want that. So let me rub this. Are you getting, guys? थोड़ा सा one AND gate, another AND gate and 1 OR gate, and that is how you can obtain the output here. And the connections would be Q1 bar, Q0 bar. Yeah, any doubt, please ask. If you have doubt, please ask. Here Q2 bar, Q1, and Q0. And of course this will be connected. किसी को समझ में नहीं आया यहाँ पे? बोलो. Is this fine, guys? हाँ? Oh, okay. So you tell me the logic. हाँ? हाँ. तो टी के लिए लॉजिक कैसे बनाओगे? अरे ये मुझे बोलो, ये क्या है? ये कौन सा काउंटर है? सीरियल काउंटर. तो क्या करना पड़ेगा? या दैट्स वेरी इंपॉर्टेंट. यू हैव टोल्ड मी वेरी इंपॉर्टेंट पॉइंट. इज करेक्ट. हाउ द इनपुट्स विल बी देयर? अरे ये serial counter है. That means what? Synchronous will do the job. So I'll simply connect the output of first to the clock of the next. That's it. And of course here I will connect it to. Now is that okay? Thanks for that. Of course there will be a master clock here and the output, single output. Yeah, sometimes I may miss such points, so you have to be attentive in the class, otherwise I will cut the marks. What is the cruel thing I can do? Cruel most thing I can do? Huh? Alright, so is this okay? Fine. So let's time nahi hai, so I'll stop here. And some important points. Now it's your exam. Today is 5th, na? So we also have a class on Tuesday, yeah? You tell me. I mean, और उसके बाद immediately exam है ना? So you want us to conduct the class or like how? Sure. Okay. So I will be available. Shall be available in my cabin. If you have doubts, please ask. I'm available via mail, WhatsApp, anything you can ask. If you have doubts, please ask. For reference, okay? For again, the second sectional examination, पहले सेक्शन का बहुत poor response था. I don't know why. You didn't practice. That's what was the reason. For practice, you can refer the recommended books, all the recommended books. Although I have disabled the link for the books, okay, you very well have that link in your bookmarks. So I hope that. For counters and shift registers, you can go for local author book, no problem. Okay, as long as logic is correct. Anand Kumar is very nice book. Okay, he's one of the experienced faculty. So I'll try to post excerpts of the chapters of counters on the website, so stay tuned to the website. There are a lot of examples, solved examples and unsolved examples. Do attend that. Next, let's quickly revise what we can expect in the sessional to exam.